So what I'm going to do is I'm going to give you the proof, or at least some main ideas of the proof of the main result. Then I'm going to move on to some open questions that at least I think are very interesting. So here's a reminder of the main result. You have a closed Riemann surface and some actions on Euclidean spheres. By harmonic map theory, you get corresponding harmonic maps, harmonic representatives. So those are maps from the universal cover to the sphere, and they're very nice, they're harmonic and equivalent with respect to the action. The conclusion is that if your actions strongly converge, then the harmonic maps look more and more like the hyperbolic plane. So one type of optimal geometry meets another type of optimal geometry. Also, I wanted to remind you of the corollary that I mentioned. So for any closed hyperbolic surface, remember the corollary was that there is a finite cover of this closed hyperbolic surface. And some harmonic map from this closed surface to some Euclidean sphere such that you're harmonic and your pullback metric is more or less 1/8 times the hyperbolic metric. I want to give you some remarks. The first remark, so if you like well-packaged motivations, let me give you a conjecture of Yau. So it's a conjecture of Xintung Yau, and it tells you that there should exist a closed minimal surface of dimension 2 in some Euclidean sphere with negative Gaussian curvature, so negative intrinsic curvature. So that's the conjecture. How is that related to this corollary here? Well, I mentioned in my second lecture that being minimal in our situation basically means being harmonic plus conformal. So harmonic is critical point of the entity. Conformal means you preserve angles. And so here you have a map which is harmonic, and you almost preserve angles because you're almost in isometry, actually. So you're up to the scaling here. So those surfaces, you can think of it as almost minimal surfaces. And clearly, the pullback metric is close to the hyperbolic metric rescaled. So the intrinsic curvature is definitely negative everywhere. The second remark. So in this minute school, I talked to some people who were thinking about eigenfunctions on surfaces. So let me tell you another consequence or another way to formulate this corollary. Sorry. So think of psi here as a map with value into a Euclidean space. So remember that being harmonic and having value in a sphere imposes something very strong, an equation of that form. Oh, I got a lot. Okay, I'm used to using U, so I'm just going to use U. So the second thing, which is that you're almost an isometry, let's think about what it means for this quantity. So if you are exactly an isometry, so if the pullback is exactly 1/8 times the hyperbolic metric, you can compute this number. You'll see that it's 1/4. So under the conditions of the theorems, you get that in the end, this is almost 1/4. So I remind you, of course, that 1/4 is the bottom of the Laplacian on the hyperbolic plane. So what that means is that you give me any hyperbolic surface, I can give you a certain finite cover of your hyperbolic surface, still closed, and some functions which are almost eigenfunctions with eigenvalue 1/4, such that they are giving a map into a sphere. So what this means is that there are such functions so this equation tells you that you have value in a sphere. In other words, the sum of the L2 densities of your functions is 1. And moreover, the functions that you have are almost 1/4 eigenfunctions. So they're almost eigenfunctions with eigenvalue 1/4. So what I think this is hard to believe. So if you know a bit about spectral theory, there's something called the local Weyl law, which tells you that if you look at all the possible eigenfunctions with all the possible eigenvalues, you do have something like this, meaning that if you take a normalized sum of L2 densities, you'll end up with the volume form. But here, it tells you that you can pick those functions to be essentially, to only see the spectrum at a very low level, 1/4. So is there any question on this thing and this remark? So somehow 1/4 here is very special. For example, I expect that over 1/4, this is always possible, and under 1/4, this is never possible. But I can only show that it's possible at 1/4. Right, so I'm going to now, if you don't have questions on that, I'm going to give you some main ideas about the proof of the main theorem. So recall that strong convergence, it means something very concrete in terms of operator norms of certain operators. So here F is any element in the group algebra. So you have this convergence in norm. And remember that what we called weak equivalence. So the definition of weak equivalence is that you have equality of norms. And I want to remind you with just words that if you're weakly equivalent, what it means is that the action here can be imitated or approximated arbitrarily well by the second action, and vice versa. So in other words, you give me a point and an orbit for the first action. There's another point somewhere else where the orbit for the second action is going to look almost exactly the same. And so that has geometric consequences that I'm not going to prove rigorously, but I hope that you're going to believe the following thing, the following consequence. And I claim that since the energy of this representation is finite, okay, this is just a claim, which is not too hard to show, by approximation, you get a conclusion about the finite dimensional representations rho j. So
The next line if you have zeros.
oh, yeah. Thanks. So why is that useful? I'm just saying that I want an upper bound on the energy because at some point I want to take a limit of harmonic maps. So we, by the existence literature, we understand well what it means to strongly converge, and I want to translate that to geometric properties about the harmonic maps that represent those representations, right? And by thinking about what the approximation property means, already you have this uniform bound on the what we call the energy of this pair, which is the energy of those harmonic maps on some fundamental domain. Once you have an energy bound, you might recall that in my my lecture about harmonic map theory, you have an epsilon regularity theorem. And I told you that it was almost a synonym of compactness theorem. It tells you that you can take a limit because the energy is uniformly bounded. So you want to take a limit of the psi j, the harmonic map there. So I told you because of that, this is more or less possible, and the rigorous way to, or less non-rigorous way to say it is that there exists a rotation of each sphere such that if you rotate the image, maybe you have to rotate the image to keep it in a compact subset or pre-compact subset. These harmonic maps are going to converge to a limiting harmonic map from the original surface to some sphere of infinite dimension. Maybe it helps the imagination to think of all the Euclidean sphere here to be contained isometrically in a given Hilbert sphere. And I'm going to summarize all the properties that we got essentially by working more on the definitions that I gave you here. So what you get in the end is that this map is harmonic as a limit of harmonic map. That's fine. All the psi j's are equivariant with respect to some action. So you expect the limit to be equivariant to by some limit action. And what is this limit action? You cannot exactly say which one it is, but at least you can say that it has to be weakly equivalent to the regular representation. And this is very important. The whole point of looking at strong convergence is that you can identify the limit action. So if you worked with weaker notions of convergence, you would not be able to identify the limit action. So this is where strong convergence is really used. The last property is that this map is actually also equivalently energy minimizing. So not only is it a critical point of the energy, it's actually minimizing the energy among all equivalent maps. And this is harder to prove, but quite intuitive, because this is just a limit of equivalently energy minimizing maps. So this is more or less step A. Let's see if there's any question.
Sorry, instead of having like energy minimizing, we just have things that are harmonic with bounded energy to work. Is that really?
I think taking the limit would work.
But then using the limit.
But then I would not be able to say anything about the limit. So that was the step where we used strong convergence. So the last two steps are going to show that this map has a very explicit form and that the pullback metric exactly what we want, the hyperbolic metric. And because of smooth convergence, we would have shown that right before taking the limit, the pullback metrics were almost hyperbolic, times 1/8. So let's see, what is the next step? The next little step is going to try to say something about the energy of this map. So I said that it was energy minimizing. Maybe I can just give you the number, the energy of this map on a fundamental domain. And this is a consequence of a result of Besson-Courtin-Gallo. I'm not going to have time to prove it, but it's a lovely argument. It's very short. So I really encourage you to take a look at the lecture notes if you're interested. It tells you that if you give me any surface, any Riemann surface here, closed, and you look at the regular representation, this invariant is completely computable and it's exactly that number. So pi/4 times the absolute value of the Euler characteristic of S. So it is strange, at least a priori, that you're looking at this infinite dimensional representations, but somehow things are much more explicit. You can compute the energy, whereas for finite dimensional representations, usually it's hopeless to try to compute exactly the value of the energy. Remember that E is the infimum of all the possible energies of equivariant maps restricted to a fundamental domain. So the higher dimensional version of this fact is essentially equivalent to the volume rigidity theorem of Besson-Courtois and Gallo, and I'm going to talk more about that in the question section. But for now, let me just say that using properties, using the definition of weak equivalence, so one can approximate the other, actually this implies, you have to show something, but this implies that the same equality holds whenever you're weakly equivalent to the regular representation. So that's good because we are not working with the regular representation, we're only working with something that's weakly equivalent to the regular representation. As I was trying to explain, this plus what I wrote there for psi infinity tells you that you can compute the energy of psi infinity on the fundamental domain is going to be equal to that number. And I'm jumping a lot of steps here. I don't want to spend too much time on the details, but you can ask me if you want to have more details. What I'm going to claim is that this number is purely topological. So this is the other characteristic. But all our problems here depend on the surface, which is a Riemann surface. So you start with a conformal class, and you do some geometric construction, you get an invariant that's independent of the conformal class. So this energy being independent of the conformal class tells you by standard minimal surface theory that not only is psi infinity harmonic, it's much better, it's also conformal. So it's a map that preserves preserves angles. In other words, or at least this implies, that your map psi infinity is a minimal map. And so this is the end of step B. OK, let me repeat a little bit what we did. So we had this sequence of harmonic maps. We wanted to know something about the pullback, so we take a limit of those maps. And we want to show that the limit map has pullback exactly the hyperbolic metric. Here we construct the limit map, and we have some nice properties, which implies that this map is more of a minimal. So we have a lot of good properties on this map. And let's think about that. What is another map that has all those nice properties that we saw yesterday? So yesterday, I talked about PSL2R representation theory. And there, we had exactly the same kind of map with exactly the same properties, being minimal, energy minimizing, and equivariant with respect to some boundary representation, which is weakly equivalent to the regular representation. So let's see. But the map that we saw yesterday, contrarily to this map, which is just obtained by some compactness result, the other map that we saw yesterday is completely explicit, and we know that for the other map, the pullback metric is exactly hyperbolic. So let me remind you a little bit what we did yesterday. So I guess this is the rigidity part of my lectures. Pullback limit. So the goal is going to show, so what we want is to show that this limit, which is obtained by compactness, is such that if you pull back the standard Hilbert metric, is exactly equal to the limit that you want to see. So if we have this, we prove the main theorem, just because of the fact that the psi j converges smoothly to psi infinity. So this is the goal of the main of the end of the proof. Okay. So let me say that together with Ricardo Cagnato and Xiang-Zhe Li, who's somewhere here, we were able to prove a much stronger statement, which is that this psi infinity is completely unique up to isometry, up to rotation of the sphere. But here I'm just going to look at the pullback matrix, the intrinsic shape. Any questions so far on this? What's happening? So unique up to rotation of the sphere, meaning that maybe you have, what does it mean? I mean that after rotating the ambient Hilbert sphere, the map becomes exactly the same as an explicit map, some explicit map, which I'm going to remind you. Oh, okay. So whatever limit you can obtain here. So here, actually, what this means is that the intrinsic geometry converges, but maybe the map themselves could behave quite chaotically. So that tells you that extrinsically also the geometry becomes unique up to rotations. What is the idea here? Again, it's to compare this unknown map with a very well-known map, the map that I surveyed yesterday. So it's this map P. So I'm quickly going to remind you what P is. It comes from representation theory. It's very classical. It goes from H, the hyperbolic plane, to some infinite dimensional Hilbert sphere. And so this map is minimal. This map is equivariant with respect to some boundary representation, which is, again, very well known. And P has the property that we want. So P has the property that if you pull back the Euclidean or Hilbert metric on the sphere, you get the hyperbolic metric times 1/8. In particular, you can compute, because of this, you can compute its energy. And it's exactly equal to this number that I copied already several times. So how do you want to compare such two maps? It's going to be a kind of interpolation argument. So if you're familiar with the case where the target space is negatively curved, say, you have two harmonic maps in the same homotopy class, you want to compare them, what do? You cook up a continuous family of maps between the two using geodesics from points on the first map to points on the second map. And you look at the energy, it's going to be a convex function. So that's great because that gives you that critical points of the energy are unique. This completely fails for spheres again, you don't have convexity of the energy under those kind of geodesic interpolations, but still we can do something that is reminiscent of this, but that really crucially uses that you are in infinite dimension. So somehow infinite dimension is your friend if you want to get some rigidity, at least in this situation. So let me try to illustrate that in a toy case. So my claim is that in order to show this, so basically what we want is we want to say that psi infinity and p are the same. This is the dream. It's enough to show something like that. And that's the meat of the second part of the proof. You take any representation, it could be finite dimensional. Consider for I equals 1 or 2 a certain map from the universal cover of S to the unit sphere of this particular Hilbert space. So H is the Hilbert space of rho, and I remind you that there's this standard construction of taking infinite direct sums that gives you a new, bigger, infinite dimensional Hilbert space and a corresponding direct sum of rows. So let's assume that you have such maps. And let's assume that if you pull back the Hilbert metric on the surface, you get a map which is a minimal map. Okay, let's say immersion to simplify the statement. Equivariantly energy minimizing, you cannot say anything about the general maps, but if you have equivariance, suddenly things are going to become rigid. So equivariantly minimizing for this action. Then actually the pullback metrics are the same. So as you can see, it's pretty general. You don't need the regular representation here. You just need to take some unitary representation which is sufficiently self-similar. So the content of this theorem is telling you if your representation is sufficiently self-similar, you look at two maps from a given Riemann surface to the sphere. If they're both, with respect to the pullback metrics, if they're both minimal emergence and equivalently energy minimizing, then actually the pullback metrics are the same. So now you can imagine, okay, how would you apply this? Well, you can try to apply this to the maps psi infinity and p, and you would get that the pullback metrics are the same. This is basically the idea, right? So I hope that you're intuitively convinced that all we need to do to show our goal and finish the proof is to show some uniqueness statement like this. What's not clear is why. So in this statement, I'm looking at infinite sums of representations, which we don't have here. I claim that you can overcome those little challenges. But let's see if there's any question on this.
So you can somehow use it. If I take an SL2R lot representation and restrict it to a surface group, then it's essentially a direct integral over the fundamental domain, and it's not going to be copied. If I I take the regular for SL2R, are restricted to the surface group, it looks to me like the direct integral over the fundamental domain.
Yes.
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 That's going to be used here.
That is applicable, but the implicit assumption here is that there exist such maps. Because in the example that you mentioned, for example, I claim that there's no even such maps. There's no such maps which are energy minimizing. And so even though it seems like you can apply it to any such sums, most of the sums do not contain such special surfaces. This is something I'm going to come back in the questions. Yeah. But it happens that, of course, in our case, we do have such maps that we're happy. OK, so this is going to be the technical part, but I wanted to present it, otherwise there's no substance. The trick first is to observe that if you look at the space of the representation, you take the direct sum with itself. It is itself. It is exactly itself, strongly equivalent to itself. Okay? So this little observation is useful because we have a map into this and another map into this. Now you can take an average. And the new map is still going to be into the correct space. So you have the first map with value in this big sum, the second map with value in this big sum. If you take this average, I will let you check that this goes into the unit sphere of the direct sum of the two big sums, which is the original space, equivalent to the original space. So the key point, which is a consequence of this, is that this average, which a priori lives in the bigger space, is actually living in the original space up to equivalence. And so this map is going to still be equivariant with respect to this action that we are fixing for this theorem. Okay. So to conclude, you want to say the following. By completely elementary computation, you check that if you know the energy of the two maps, you know the energy of the third map. So since both phi1 and phi2, they are energy minimizing, they have the same energy. And so you get that the energy of this third average map is the same. And moreover, so another easy thing to check that is that since your minimal immersions here, you're conformal. So you're harmonic and conformal. And I'm saying that if phi1 and phi2 are conformal, then phi3 is conformal. So this board is easy, I claim. So because, remember, so phi1 and phi2, they're energy minimizing. So this energy is the minimum possible among the equivariant maps. So that means phi3 is also energy minimizing. equivalently as usual. In particular, it's harmonic. So this is the important point. So now you have a harmonic map, which is also conformal. Again, that means you're minimal. So in the end, what we have, so we have those two maps satisfying something. I want to show that the pullback metric is the same. This proof is telling you that necessarily you can cook up an average map. And all those three maps are minimal maps. I remind you that if you're a minimal surface inside a sphere, you satisfy something like this. So coordinate-wise, for each j, 1, 2, 3, for each of these maps, look at any coordinate is going to satisfy this equation. So now we can conclude, because phi 3 is a kind of mixture of phi 1 and phi 2. This minus 2 is a fixed number, but you're taking the Laplacian with respect to phi 1 or phi 2 or phi 3. And if phi 3 satisfies this equation, it has to imply exactly the conclusion, which is all those maps have the same pullback metric. So this is, again, an elementary computation, but that finishes the proof. Very good. So this is the end of the proof of the theorem. Once you know how to compare maps that are energy minimizing and minimal like this, you can apply that to P and psi infinity. So P, you know what the pullback metric is. It's that. You conclude that the pullback metrics for psi infinity is the same, and that concludes the theorem. All right, so is there any question on the vague ideas of the proof?
I'm somehow a little confused about how you go from this theorem to the conclusion, and I don't have a good question yet.
Two.
How you go from this theorem to the conclusion we want about our sequence? Like I know.
Okay. So once you know that, so what you conclude using this blah blah is that you get this, right? So you get that the pullback metric of this limit map is 1/8 times the hyperbolic metric. Let me remind you that the main theorem, the conclusion was you want that psi j, when you pull back the Euclidean metric, converges to exactly this. So you have those harmonic maps into finite dimensional spheres. You want to know what the pullback metrics are going to converge to. So one way to do this is you take a limit of those harmonic maps, and if you can identify exactly what's the limit pullback metric, you conclude. Okay, I have 10 minutes. I want to... Sorry, it's hard for me. Yeah, so those maps, they're all conformal. So these maps, you can write them down as maybe some conformal factor times a fixed metric, G0. You don't care which metric it is. So it's known that if you take the Laplacian with respect to a conformal metric, it's equal to the original Laplacian with the original metric times this function. And in our case, we have two half of the coordinates. The first half, you're going to see F1 coming out. The second half, you're going to see F2 coming out. The only way it's one function is that F1 equals F2. Okay, so this is the end of the proof. I want to give you a one-line summary, and I'm going to move on to questions. Okay. So the summary of all of this is that in our setting, under random equivariance constraints, minimizing harmonic maps into spheres look like a hyperbolic plane. And in the proof, what we saw is that having things at random or high dimensions you get more rigidity. So in some cases, again, you don't need any of that in negative curvature and things like this. But in our case, we're looking at the complete opposite, where you're looking at harmonic maps with values in spheres. And what I'm saying is that if you throw in some randomness, or if you look at very high dimensions, somehow paradoxically, you get a much more rigid picture. So of course, this thing about randomness should be very familiar with people in dynamical systems. But here we saw in this proof that being infinite dimensional was actually crucial for the argument to work. So the conclusion of this would be false if you, I don't know if it's false, but would probably be false if you replace this infinite sum by a finite sum. And I want to finish quickly with some questions, as much questions I can write down in 5 minutes. So first, let me fix a notation, which is instead of looking at surfaces, you can generalize those definitions at least to any closed manifolds. And so if you give me a closed manifold of any dimension and a representation of I1, a unitary representation in some Hilbert space, you can always define the area of this pair. So in general dimension, it's more natural somehow to look at the area instead of the energy. So it's very similar to the energy, except that you look at the area of the pullback metric. So you look at the universal cover of M, the fundamental domain, and you compute the area of this with respect to the pullback metric. Okay. So here it's over, the infimum is over all U smooth maps from the universal cover to the unit sphere of H rho equivariance. So the first question is, I'm really interested in computing the value of this, say for M asymmetric, locally symmetric space. Let's say it's irreducible, symmetric, high rank, of non-compact type. The invariant I'm extremely interested in is this. And the reason is that there's a conjectural value, which is essentially the volume of M with respect to the well-normalized symmetric metric. And if the conjectural value is indeed that invariant, you get entropy rigidity, so at least the inequality, and then probably the rigidity part. For M. So remember that, I want to give some names here. Besson-Courtois-Gallo, which we saw already earlier, what they showed is that in rank 1, they can exactly compute this quantity. And it's exactly what you expect. For example, if M is a hyperbolic manifold, this number is the hyperbolic volume times the dimensional constant. What this implies is their theorem on volume entropy rigidity. So I'm explaining that in the lecture notes, and you can take a look if you're interested in this relationship between, say, those kind of invariant areas and the volume entropy invariant.
Are you saying there is an explicit conjecture? If I give you a particular high-rank symmetric space, there is some conjecture?
Yeah. So the conjecture is that, I mean, I always forget the coefficients, but there's a dimensional coefficient times the volume of the symmetric metric, so normalized symmetric metric. So these kind of ideas first appeared in the original paper of BCG in French, and later the surveys in English do not contain those ideas, so you lose a little bit in translation. So what remains in their translations are, okay, the barycenter map. So you hear a lot about the barycenter map. My claim is that the barycenter map is just one possible way to show that to compute this invariant, to show that a certain embedding is area minimizing. But you have more. Why do I want to state that? I want to maybe encourage people to think of maybe other ways to show that something is area minimizing, because the barycenter map is just one way. Maybe you have other ways, for example, calibrations, more general calibrations. Okay. Okay, the second question is also about higher rank, trying to adapt to the audience here. So M as above. My question is the following. Is there a C such that for any non-trivial unitary representation, you can guess the conclusion? You have this. While that question is, I know, extremely hard, I don't know if this question is trivial or not, considering all we know about high rank. But I want to point out that we can think of those kind of invariants as higher dimensional versions of the Kazhdan constants, the usual Kazhdan constant that you use to describe property T. So for property T, you look at a given unitary representation. So you fixed yourself generating set of your group, and then you look at the minimum of some sum, right, of distances, essentially. So the Kazhdan constants are really about one-dimensional information, so a sum of distances. And here, this is basically a sum of areas. So you get an area. It's n-dimensional. So you have variants of this question where you play around with the M here. So again, this would be a kind of higher property T, but with respect to those kind of higher dimensional Kazhdan constants. And I only have time for one more question, so let's go. Which one do I want to present? I'm very interested in the distribution of the images. Now I'm coming back to dimension 2 of the harmonic maps I talked about. And I'm interested in both when the dimension goes to infinity or when you fix a dimension. So here's the general motivation. For example, in dynamic ecosystem, if you look at closed geodesics or almost totally geodesic surfaces in hyperbolic manifolds, you're very interested in the limiting measures. For example, for almost totally geodesic surfaces, there's this conjecture of Kahn, Markovich, and Smilga that tells you what the limiting measures should be if you take an average. It should be the uniform measure somehow. And so this is the kind of questions I want to understand, which is, okay, if you pick those harmonic maps at random, what is the distribution of the two-plane in the sphere? And either for fixed dimension or when the dimension goes to infinity. All right, so I think I'm going to end with that. Thanks a lot for your attention. And by the way, so I want to, on behalf of everyone, so thank the organizers, so Fanny, Matthew, Ralph, and David for organizing this wonderful mini school and making us all very exhausted.